Hello everybody, welcome back to Cumulative Review number 15. In this video we're going to be going over numbers 7, 8, and 9. So if we start with number 7, the directions are to condense the log expression to a single logarithm. So we only want one log in the end. And the first thing we'd like to do when we're condensing is move all the leading coefficients back up to be exponents so that we can make it even smaller. So we'd have log of x plus 1 to the 1/4 minus log of y minus 2 to the 9th minus log of z to the 3/4 power. So at this point, there's two ways to think about this problem. If you'd like to go to a single log, some of you might look at the first two and say log of something minus log of something means that this is in the numerator and this is in the denominator. And then you might continue to think if this is being subtracted as well, this also has to be in the denominator. So some of you might jump straight to this, log of x plus 1 to the 1/4 over both y minus 2 to the 9th times z to the 3/4 power. Now, some of you, if you don't want to jump directly to them, you could think of this step in between. The blue is really the same as log of x plus 1 to the 1/4 minus all of, if you take the negative out of both, log of y minus 2 to the 9th plus log of z to the 3/4. The reason this might be helpful for some of you is what you're doing is you're taking a log minus a log. And so this makes sense that it's in the numerator, but because all of this is being subtracted, that's why both of them are in the denominator. And the reason this is multiplication down here is because these two logs are technically being added if you take out the negative. So it doesn't matter. If you want to go directly from the blue to the red, that's fine. If you prefer to go from the blue to the green to the red, that's fine. But this still isn't the final answer, because I would like to write all of these as radicals if possible. So we'd have log of, so instead of to the 1/4 power, that is the same as the 4th root of x plus 1 in the numerator. Then we still have y minus 2 to the 9th in the denominator times. Now let's think about what this means. This 4 meant 4th root, so this 4 also means 4th root. So that means I have a 4th root of, now this 3 on the top means I'm raising it to the 3rd. So it would be the 4th root of z cubed. So my final answer is a single log with the 4th root of x plus 1 in the numerator, and then these two pieces in the denominator. Number 8. The directions are the opposite. You want to expand the logarithm, and the reason that I put these next to each other is they do end up being opposites of each other in a way. So notice that first, before I begin, that I'd like to expand. So I'd like to get multiple logs, kind of like how this one started. Also, please notice that all of these are being raised to the 1/2 power, or all of them have a square root over it. So the first thing I'm going to do is write this as log base 4 of x cubed over y to the 6th times z, all to the 1/2 power. What that means is that this 1/2 power can come down in front. So I'd have 1/2, and that 1/2 is going to be affecting everything I do. So if you think about it, the 1/2 has to be in front of everything. So it'd be 1/2 log base 4 of x cubed over y to the 6th times z. Now the directions are still to expand. So what I have to do is think about how this relates back to this problem. If I see an x cubed in the numerator, that means I start with it. And if I see both of these in the denominator, if you think about the previous problem, if two things ended up in the denominator, they came from two logs that were subtracted. So here's what I do. This 1/2 has to affect everything I do. So we'd have 1/2 log base 4 of x cubed. Then we'd subtract 1/2 log base 4 of y to the 6th, because this is in the denominator, so it's being subtracted. The z is also in the denominator, so it is also being subtracted, and the 1/2 applies to this as well. 1/2 log base 4 of z. Now, am I done expanding? No, because all the exponents have to come back down, if there is one. So this would really be 3 times 1/2, or 3/2, log base 4 of x, bring down the 6. That's really the same as 6 times 1/2, which is really 3 log base 4 of y. And this one does not have an exponent. It does, it's 1, but it makes no difference. So 1/2 log base 4 of z. And so we've expanded this. And I again would like to point out to you that these are inverses. This answer looks very similar to how this one began. And this answer looks more complicated than this one. But the reason I put this problem on here was to remind you what to do with that 1/2 in front. Last one. The next video set starts with number 10, so I will not be doing that on this video because that's on the next one. So I'm going to end here with number 9. And the goal of number 9 is to see if I have to use logs or if I can get away with not using logs. So what I would do is look at the two bases that you have and ask yourself, can you write 8 and 32 as a different base or as something to a power? When I look at 8, I think about that could be written as 2 to the 3rd power. Could 32 also be written as something or as 2 to a power? Yes, it can. 2 to the 5th power. So, what we really have here is if you replace 8 with 2 to the 3rd, we have 2 to the 3rd times 5x plus 1. We have 2 to the 5th times x minus 3. And so if your bases are the same, that really means that your exponents have to be equivalent or equal. So you really have 3 times 5x plus 1 equals 5 times x minus 3, which would be 15x plus 3 equals 5x minus 15. And if you solve this, you would get 10x equals negative 18. Divide both sides by 10. X would equal negative 18 tenths, or if reduced, negative 9 fifths. Now let's say on the test you didn't see that. You didn't see that you could change the bases. You could also use logs to solve this, so I thought I'd show you that as well in this video. 32x minus 3. So what you could do is you could take the ln of both sides instead, because the inverse of an exponent is a log. So if you want to take the ln or log of both sides, you would have this. And if you have a log in the problem, you're allowed to bring the exponent down on both sides. So you'd have 5x plus 1 times ln of 8 equals x minus 3 times ln of 32. And then what you could do is you could get all the x's on one side and you could get all the ln's on the other side. And to do that, you would create something that's cross multiplication, because what I would do is move the x minus 3 over here by dividing. So you'd have 5x plus 1 over x minus 3 equals, then if you divided the ln of 8 over here, you'd have ln of 32 over ln of 8. And then you could go through and cross multiply and solve this. Now, as you can see, this way is a lot more complicated than the first way that I did it, so it's good to look for the bases first. So what I do at this point is actually divide these two things so the cross multiplication is easier. So you do ln of 32 divided by ln of 8. That's 1.67 repeating, or 1.6 forever, equals 5x plus 1 over x minus 3. And you think of this as over 1 because you divided these two. Now it might be easier to cross multiply. So you have 5x plus 1 equals 1.67 times x minus 3. Then you could distribute this in. 5x plus 1 equals 1.67x minus 5.01. So if we continue this, let me extend the page. We would have, if I subtracted 1.67 over, I'd have 5 minus 1.67, which would be 3.33x equals negative 6.01. And if I divided both sides by 3.33, I would have x equals negative 1.804 about. And if I go back and look at my previous answer, and if I take 9 divided by 5, that is really x equals negative 1.8. So these two answers, in my opinion, are equivalent. The reason they're not exactly the same is because I rounded this. This was really 1.6, or it was 1.6 repeating. So because I rounded that, this answer was a little off, but the method is correct. So because these answers checked out, these are both legitimate ways to solve the problem. My suggestion for your test, if this comes up, please consider doing method 1. It is much faster. All right, thanks guys.